All right, so where are we at? There's more to this one than I thought. Okay. So reabsorption regulation, okay? Like so many things in the body, if we're going to do a thing, we're going to have to regulate it. All right, so some key factors about regulating tubular reabsorption. Okay, first off, as GFR increases, the amount of filtered solute also increases. I think that makes sense. The more you filter, you don't get just water, right? You also get solute. So it means that when GFR increases and the filtered solute increases, reabsorption rates also have to increase, right? So there needs to be a way for the kidney to up its reabsorption gain when GFR increases, right? So the first limit on that is the glomerulotubular feedback mechanism we talked about the other day. It is tending to keep GFR for a particular nephron in a relatively narrow range, right? So for a given nephron, that nephron's GFR, while it can increase or decrease, it's going to stay pretty consistent over time because of the glomerulotubular feedback mechanism, okay? So this prevents the need for the cell to have to dramatically, or the nephron to have to dramatically increase or decrease its reabsorption. So at least that slows it down. It's a stabilizer, right? So the cell can kind of do the same thing all the time and keep the GFR in its range instead of the other way around. The peritubular capillaries also play a role in regulating tubular reabsorption. Okay, so when blood pressure goes up and hydrostatic pressure goes up, all right, that's going to increase GFR. Okay, we've already learned that. But in the peritubular capillaries, we get an increase in hydrostatic pressure that reduces the reabsorption pressure. So essentially, as GFR increases, it is easier for molecules to be reabsorbed into the peritubular capillaries. The easiest way to think of this is the more pressure you used up to create glomerular filtration, the less pressure there is in the peritubular capillaries, right? So in other words, they're going to tend to have, it's going to be easier for materials to enter the peritubular capillaries. Then we get the afferent and efferent arterial business, right? So an increase in resistance of either afferent or efferent will reduce hydrostatic pressure in these capillaries. We turn the valve down, right? So less blood is entering them. That increases reabsorption. And then that last point, let's see. Oh, just in general, forces that tend to increase capillary reabsorption also tend to increase tubular reabsorption because it's the same processes, right? It's just like the material in the nephron tubule, in the lumen, it's undergoing many of the same forces that we encountered in the capillary, right? So I think of this particular point as a fairly deep and esoteric concept, which I'm not terribly interested in you knowing a ton about, right? Short version is this. The more glomerular filtration we have, because of the same factors in the system, the greater the reabsorption we have, right? So as filtered solute load increases, reabsorption also increases, is the clinically relevant version of this. I struggle with this bit because there's some piece of it I can't wrap my own head around, despite years of trying. So we just sort of keep it at the clinical level. All right, so many of these players, all of these players we have talked about before, they each have an effect at reabsorption and secretion. Okay, aldosterone we've talked specifically about, right? Collecting duct, tubule, and duct. Notice it does not say proximal convoluted tubule, right? The proximal convoluted tubule's sodium-potassium pumps are always on. The aldosterone-sensitive sodium-potassium pumps are on sometimes and not on other times, okay? So we only find those in the distal convoluted tubule collecting system, in the regulatable sections. And what does it do? Well, it's going to increase sodium and water reabsorption and potassium secretion. Aldosterone does have an effect on hydrogen ion secretion. We're going to talk about that in our acid-base talk, okay? It's an exchange that happens when your potassium is high. Angiotensin II, from the famous renin-angiotensin-aldosterone system. Okay, its effects are similar. Increased sodium chloride and water reabsorption, increased hydrogen ion secretion. Antidiuretic hormone works to increase water reabsorption, particularly the collecting system. And then our atrial natriuretic peptide, remember that's comes from the atria when your venous return is too high, right? Atria gets stretched, releases ANP. It's a sign of too high plasma volume, right? So the response to atrial natriuretic peptide is to decrease sodium chloride reabsorption, again, in the distal tubule, the regulatable section, right? So ANP has its effect at the same place. By reducing sodium chloride reabsorption, we increase water excretion, right? If we pull in less salt, less water follows that salt, so we end up with more water in the urine. Parathyroid hormone also has an effect at the distal convoluted tubule, but its effects are entirely about phosphate and calcium. Remember, parathyroid hormone is our calcium regulator. Phosphate goes with calcium because of bone. Okay, so when we release calcium from the bones, we also get phosphate, which we typically don't need. Well, parathyroid hormone will decrease phosphate reabsorption and increase calcium reabsorption. So when parathyroid hormone triggers calcium release from the bone, that calcium is held onto in the kidney, and the phosphate that comes with it is dumped. Its reabsorption is decreased, and therefore its excretion is increased, right? So parathyroid hormone effects on this system. Okay, so aldosterone in particular is going to affect the sodium-potassium pumps, both the number and the amount of activity they have. So when aldosterone is present, we get more of those pumps. More of those pumps is more sodium retention. Sodium retention leads to water retention. Now you can also see the potassium side of things, right? So aldosterone is secreted in response to low plasma volume. Okay, that triggers the sodium retention. But this is the weird one. Aldosterone is also released by a completely separate mechanism due to high potassium levels, regardless of what your plasma volume is, right? So you could be very, very wet and have a high potassium level, and your aldosterone will still be high, right? Because you're dumping potassium. Now, is that good for you? No, because you're also absorbing water, right? Now, so how do we escape that? ADH, right? Because ADH can affect water without affecting salt. When we have that situation of a high potassium level, we get aldosterone is high to excrete the potassium. Sodium, yes, is reabsorbed, so we end up with an increase in or a decrease in urine output. But then ADH comes along and makes the urine dilute, so that we can still get rid of the excess water even though potassium is high. So it's kind of a weird interrelated system. It's one, I haven't said this to you guys yet, but if you were going to redesign the human being, you would have an aldosterone for sodium and then something different for potassium, right? Because then you wouldn't have this problem of a cross reactivity. Okay, that's aldosterone. What does angiotensin II do? So it's going to stimulate aldosterone secretion, right? And that's going to stimulate sodium and potassium pumps like we just talked about. AT2 also works on the pressure side, works on the filtration side. Okay, so it's going to constrict efferent arterioles. That's going to increase glomerular hydrostatic pressure and GFR, right? Angiotensin II directly stimulates sodium-potassium pumps throughout the nephron, okay? also stimulates sodium hydrogen exchangers, and directly stimulates the sodium bicarb exchanger. So angiotensin II is a busy thing, right? It basically is it almost works like epinephrine a little bit for the renal system for plasma volume. You know, in other words, it does a lot of things that all have the same goal, which is to increase blood pressure and hold on to plasma volume. All right, and then ADH. ADH's one job is when ADH is present, we get this cyclic AMP attached mechanism that stimulates the formation of aquaporins. Aquaporins get installed in the membrane, and now the cell is water permeable. Now all cells have aquaporins. What makes these cells unusual is they only have aquaporins if AVP is present. Okay, if ADH is AVP, it's the same thing.